Hello students, this video is brought to you by Site India e-learning. To join online classes from anywhere and offline classes only in Lucknow, please click the link to see contact information. Thank you. Today we will discuss first law of thermodynamics. Before it I have explained work done by a thermodynamic system and PV graph. Okay. Today I will start from a cyclic process. What is a cyclic process? Cyclic process. What is a cyclic process? There is some thermodynamic state. Thermodynamic state, say a state of a thermodynamic system, say gas, having particular volume at particular temperature and pressure. We can understand it using PV graph. This is V and this direction P, pressure. Suppose a thermodynamic system is in state A. This system, if occupies different volume at different pressure and temperature, then its thermodynamic state is different. Suppose it is in another thermodynamic state B. So this is one thermodynamic state, this is another thermodynamic state. This system can go from state A to B via any path. Say this goes from A to B by this way, A to B. If it returns to A state, state A again, this is returning to state A again, then this is a cyclic process. That is, in cyclic process, thermodynamic system starts from state A, say A, undergoes other states and returns to its initial thermodynamic state, then the process is cyclic process. Okay. So I think it's clear what is cyclic process. A work done in a cyclic process. Work done in a cyclic process. Okay, suppose when the system is in state A, its volume is something. When it returns to state B, its volume is different. Say it is V1, it is V2. When system goes from state A to B, then work done is by the system because volume is increasing. Obvious है कि volume is increasing. So A to B work done होगा area enclosed by the graph with volume axis. That is this area. This area is in going from state A to state B. Okay. So this area gives the work done by the system in going from state A to B. Now, system is returning from B to A. So work done will be area enclosed by graph with volume axis. That is this one. This area is the work done on the system. Here work is done on the system because volume is decreasing. This checked portion is the work done on the system and this whole is work done by the system. तो net work done by the system कितना होगा? Obvious है. Net work done by the system. Whole area work done by the system. Checked area work done on the system. So net work done is the whole area minus checked area. What is left? This enclosure, this cyclic graph, enclosed by the cyclic graph. So area enclosed by cyclic or say closed graph, cyclic graph. So this area gives work done by the system or say work done in cyclic process. Work done in cyclic process. One thing we should understand that if cyclic process is clockwise, then which is this, work is done by the system. Maybe cyclic process is anti-clockwise. This may go via this path. Then work is done on the system, and which will be negative. If work is done by the system, it is taken positive. I have already told you. Okay. Now, in cyclic process, work done by the system or on the system, we can directly find using the area enclosed by the graph or say cyclic graph or say closed curve. It's okay. Now we will discuss what is internal energy of any substance, of a body or say of a thermodynamic system. We see that any substance is made up of molecules and there is force of attraction between the molecules. Due to force of attraction, molecules possess potential energy. Any body, if it possesses potential energy, then some force is acting on the body. In the absence of force, body will not possess potential energy. The cause of potential energy is force of attraction or repulsion acting on the body. Okay. So at this time we are discussing molecules only, not the whole body. Okay. Internal energy is the something which is internal to the body, that is due to the molecules of a body. So molecules or say particles of a substance or body have potential energies due to force of attraction or mainly force of attraction acting between the molecules. And molecules are also in motion. They may be in rotational motion, they may be in oscillatory motion, in vibratory motion. So there are many types of motion in molecules depending upon it's a monatomic or biatomic or polyatomic gas, say. That is, if molecules are in motion, then they possess kinetic energy. Okay. If they are exerted by force or attraction, then they possess potential energy. So then molecules possesses potential energy as well as kinetic energies, and sum total of these two energies is called internal energy of a substance, of a body or say of a thermodynamic system. Internal energy. It can also be called thermal energy. Thermal energy. This is the energy by which molecules vibrate, do different types of motion, rotatory, translatory or vibratory motions, and these three motions gives them kinetic energies. It's okay, I think. Internal energy is the sum total of kinetic and potential energies of all molecules of a body or a thermodynamic system. Now, what is an ideal gas? In ideal gas, force of attraction between the molecules is 0. Force of attraction 0. If force of attraction between the molecules is 0, then there will be no potential energy in the molecules. So internal energy, we can represent internal energy by U. U will be sum of kinetic energies of molecules because there is no potential energy. So summation Ke of molecules. This is the case for an ideal gas. So in ideal gas, internal energy will be sum of kinetic energies of molecules because there is no potential energy in the molecules due to zero force of attraction between the molecules. I think internal energy should be clear. Internal energy is directly related to temperature. Whenever temperature increases, kinetic energy of molecules increases. That's why internal energy increases. And vice versa. If heat is given to a system, then its internal energy will increase. If heat is taken out from the system, its internal energy will decrease. Suppose a system is going from state A to B. After giving heat, then in state A its internal energy is UA. In state B its internal energy is UB. It's not necessary that all the given heat will be utilized or used in increasing internal energy, but if heat is given to the substance or say system, then its internal energy will increase. Obviously UB will be greater than UA, or change in internal energy delta U will be UB minus UA. If heat is taken out, then UB will be smaller than UA. In this case, change in internal energy will be UA minus UB. So you have to keep in mind, if internal energy increasing, then final internal energy will be greater than the initial, and if decreasing, then final will be less than initial. Okay. Now we can understand first law of thermodynamics. First law of thermodynamics. A system, thermodynamic system, suppose is in state A. A thermodynamic system is in state A. It is going to state B. Obviously, either after taking heat or after giving out heat. We should consider it with the help of a PV graph. V P, pressure in this direction, there is pressure P. System is in state A. There is another state B of the same system. It can go from state A to state B this way, via this path, via this path, via this path, via this path, via this path. There are infinite ways a system can go from state A to state B, but you will see that in each path, via each path, heat given will be different, and work done, I think it's clear. If this system goes via this path, then work is done by the area enclosed by the graph with volume axis. Via this path, work done is more because area is more. Via this path, work done is less than previous. Via this path, work done is again less. And via these paths also you can consider that area is different. That's why work done is different. How the system does work, from where, using which energy the system does work. Obviously, the heat given to the system, or sometimes internal energy of the system can be used in doing work. Obviously, in going from state A to state B, heat given or taken out will be different. Work done by the system or on the system will also be different. But change in internal energy will be same, constant. It may go via any path, but change in internal energy will be same or say constant, because in state A, internal energy is UA. In state B, internal energy is UB. What will be the change? Delta U will be UB minus UA or UA minus UB, depending upon the heat given or taken out. Here we have taken that volume is increasing in this example. That's why work is done by the system. Hence we have to supply heat to the system. Okay. Now, if we give Q heat to the system, we have given Q heat to the system. Some part of this given heat will be utilized in doing work, which is given by the area enclosed by the graph with volume axis. So some part is used in doing work, W, and remaining part is used in increasing the internal energy. Here I am saying that heat is given to the system. That's why I am saying that remaining part is used in increasing the internal energy. So some part in doing work and remaining part is used in increasing the internal energy. Okay. So it's simple. If Q heat is given to a system, some part of this energy is used in doing work and remaining part is used in increasing the internal energy of the thermodynamic system. This is first law. First law of thermodynamics says, if some heat is given to a system, then some part of this heat is used in doing work and remaining part is used in increasing the internal energy. We can write this in this way: delta U equal to Q minus W. This is first law of thermodynamics. W can be positive or negative depending upon work done by the system or work done on the system, and Q, whatever it be, Q can be calculated using formula Q equal to ml or Q equal to mc delta T. Work done can be calculated using formula P into delta V. ml, Q is equal to ml is used when there is change of state, and Q is equal to mc delta T is used when there is rise or fall in temperature. But there is no direct formula to calculate delta U. We should know Q and W, and using this formula we can calculate delta U. Okay. So I think what is first law of thermodynamics, it should be clear. Thank you.